So with the Claisen, instead of reacting an aldehyde, two aldehydes, two ketones, different aldehydes and ketones, here I'm starting with two esters. Just esters in there, okay? Now, it's a Claisen condensation. It's called the Claisen condensation whenever the two esters are the same. And it's called crossed or mixed Claisen whenever the two esters are different, okay? The only difference here, there's one difference. And the difference here is that one of the ORs of the ester leaves. So OR is a leaving group in this case. Although it's not a very, very good leaving group, but it is a leaving group in these types of reactions. So one of the ORs, not both, one of the OR of one of the ester is going to leave. This is the difference between aldol and Claisen condensation. I'm still using a base. The best base to use is the NaOR. This is the best base to use for Claisen, but the Claisen can also work with NaOH. So I can use NaOH as well. Okay, base in there. So, but most of the bases that you're going to use for Claisen is going to be NaO ethyl. This is the base that you're using. The reaction goes by either two steps or one step. It really depends. Every time you add a base, you need to add a solvent. Okay? Now, the solvent can be either H3O+, which is water in presence of an acid, or you can do, or instead, if you don't want to use H3O+, you can do NaO ethyl in presence of ethanol. But the point is that whatever comes next after the NaO ethyl needs to be a solvent. So the solvent can be either H3O+, or it can be the ethanol in there. It really doesn't matter. If you're using NaOH, it's better to use water as a solvent in there. But here it's like, it's obvious that I don't have a solvent in the first step, but whatever comes next, if this is the case, then this is going to be a solvent. I'm saying this because I don't want you to be confused between the reaction of ester hydrolysis in acidic medium and a regular solvent. If the base doesn't have a solvent next to it, then whatever comes next needs to be a solvent in there. Okay? So the reaction goes as such. Always the ester is in excess. So here we're starting with two esters. This is why we're calling it Claisen condensation. The first ester is to form the enolate from. So the base is going to come, take the alpha hydrogen of the ester, and the enolate is formed in there. And then once you form the enolate, then you do have the attack of the second ester. So the enolate attacks the carbonyl of the second ester. It's the OR of the second ester that is going to leave, because here, see what's happening. The negative charge nucleophile is attacking the carbon of the carbonyl and forming a negative charge on the oxygen. So that is going to force, this step is always a must. It doesn't happen in aldol condensation, but it happens in Claisen, where the O is going to form a double bond and the O ethyl is going to leave. I'm still having the second O ethyl of the second ester. It's right. I'm still having it, but one of the O ethyls has to leave in there. So when the O ethyl leaves, the solution is going to be more basic. Okay? The solution here is going to be more basic. I mean, it was basic and O ethyl left, so the solution is more basic. So I'm going to form here a carbonyl, and I'm going to form this product in there. But because see here, you don't have E1CB. This is not an aldol condensation, but you have something else. Here you have something else because your medium is basic. It stays basic. So that base, it's going to come and attack any acidic hydrogen. Here, I do have an acidic hydrogen between two carbonyls. So this is an acidic hydrogen. So that base has to come and attack it again. So I don't have to say that the base is in excess. The base is always in excess. in there. So the base is going to come and attack again and form the enolate. This is why the solvent is a must. So once you get your enolate in there, the solvent is going to return it back to its final product. Okay? So the reaction without the solvent stays at the enolate, which is not a product. So this is why the solvent here is a must. And this one acts as a solvent. It does not hydrolyze the esters, not yet. It just acts as a solvent and protonates the enolate and get your final product, which is exactly the same as the product that you got up there. But it's just like multiple additional steps. The reaction stops here, unless you want to go ahead and add more reagents, okay? So let's say, for example, if I take this final product and I go ahead and add an additional H3O+. This is ester hydrolysis in acidic medium now. So that is going to hydrolyze just the ester part, and the ester part is going to be turned into a carboxylic acid. I can do heat, lose carbon dioxide here because I have the condition of 2 carbonyls separated by 1 carbon, and one of the carbonyls is the carboxylic acid. Then you're going to get your product. Or I can go with ester hydrolysis in basic medium. Instead of doing H3O+, I can do NaOH, I can do water, I can do heat. And this is the base hydrolysis of ester. And in this case, I'm going to form the base of the acid. Then I would need to add an additional H3O+ and make it an acid. And then with heat, I would get the same product as well. So if I want to combine all of these steps, you're going to see them like this. Okay, in your problem sets and in your homework, you're going to see them like this. No owl for this one, by the way. There's no owl for this one. It's just like one assignment and top hat. So you start with your base. So this one acts as a base here. So you start with your base. Whatever comes next is the solvent in there. And then additional now H3O+. This is to hydrolyze the ester. So I can do it in either acidic medium or in basic medium followed by an acid, and then do heat. Heat means I am losing carbon dioxide. So this is going to be the overall reaction. Another example of a Claisen condensation. Now I've put everything together. So see here, I do have my base and I do have my solvent in this case. They are next to each other. So every base should have a solvent in there because the solvent is a must here. So the base is going to come, take the alpha hydrogen of the ester, create the enolate, and we're going to react it with another ester in there, form a negative charge, and then the negative charge is going to close, and the O-ethyl is going to leave. So your product is going to be an O-ethyl in there. The O-ethyl is going to come again and take the alpha hydrogen, which is acidic between both carbonyls, create the enolate. So this is why you have the solvent, just to protonate and return that hydrogen back again. So the hydrogen here is returned back again. Okay? This is the end of step 1. So see, all of those are step 1. So that is the product of step 1. Continue because I do have step 2. I'm doing hydrolysis in basic medium. So I'm hydrolyzing the ester into the base of the acid and then doing H3O+, turning this into a carboxylic acid, doing heat, taking carbon dioxide out and getting the final product. Look at it. Any questions on this? Okay. If you have esters that are different, then the reaction is going to go exactly the same, but now it's called crossed or mixed Claisen. In these types of reactions, I'm always going to make sure that only one ester has the alpha hydrogen and the other ester does not have the alpha hydrogen. So you don't have to go ahead and be confused. Which alpha hydrogen are you going to be taking? So this is an alpha hydrogen here. This ester has no, so here there is no alpha hydrogen. So this means that you are starting with this ester there. the base is gonna come. So notice here, notice how did I write it? So this is the base. H3O plus here is just like a solvent. It acts as a solvent because the base has no solvent next to it. So the base is gonna come, take the alpha hydrogen, make the enolate. The enolate is gonna attack the carbon, form a negative charge. And then always with Claisen, you are forming a leaving group. You are making a leaving group in there by a simple resonance, forming a negative charge. Negative charge forms a double bond, and then the OR is going to leave. When it leaves in there, this is the O ethyl. It left, right? So this means that you are forming the O ethyl again. This is a base. So this is why the base is gonna come, take that alpha hydrogen and create the enolate. So you would need a solvent, H3O plus here again. This one acts as a solvent, just protonates the enolate, and you're gonna get your final product in there. Of course, I could continue. I could use another H3O plus and I would hydrolyze that ester into a carboxylic acid and then do heat and take out the carbon dioxide. This is another example, same thing in there. This is an example, oh, by the way, this is an example between an ester and a ketone. And in this case, so this is an example between an ester and a ketone. Whenever you have an ester in there, not a diester, an ester in there, this is called a Claisen condensation. So that is going to be a Claisen condensation, not an aldol, it's a Claisen. This means that I'm not doing the E1CB at the end, okay? Because at the end, I'm not going to end up having an OH to start with. So E1CB is done whenever you have an OH in there. But I won't have an OH in there, so I'm going to call this a Claisen, mixed Claisen condensation or crossed Claisen, and it's not an aldol condensation. Here I do have two options. I do have two alpha hydrogens. Go with the one which is more acidic. The more acidic is the alpha hydrogen of the ketone instead of the ester. So this is why the base is going to come, take the alpha hydrogen of the ketone in there, form a negative charge. Before we started chapter 20, I gave you a table for the pKa's of the alpha hydrogens of the ketones, of the aldehydes, of the esters. This you can have it in the exam, and I'll include it in the exam as well. Okay, so the OR is going to come, take the alpha hydrogen, form the enolate. Now the enolate is going to attack the carbonyl of the ester, form a negative charge. Again, this is a Claisen condensation, so you have an OR leaving group. You have an OR leaving group in there, so you should have this. This is a must in there. You don't have an OH, it is not an aldol condensation. So once this happens in there, I need to, because the O ethyl is going to leave. So if it leaves there, it's here. So it's a base. So it's going to come and take the alpha hydrogen between the two carbonyls, form the enolate. This is why you need to protonate and get the final product in there. Okay, so here, this one I cannot do anything with because it's just two carbonyls. So this is it, and you stop. Another example of crossed Claisen here, I do have two esters. And as I said, if you have two esters, just one of them will have the alpha hydrogen. So this one over here is going to end up having the alpha hydrogen. This one here has no alpha hydrogen. Okay, so no alpha hydrogen. So the base is going to come, take the alpha hydrogen, get the enolate, attack it with the other ester, form a negative charge, and then allow the O ethyl to leave. This is a very important step in Claisen. Form your product in there, but the O ethyl is going to come and attack the alpha hydrogen again, form the enolate, and then with any solvent that is going to be protonated, and you're going to end up getting the hydrogen in this case. Let's go ahead and put the hydrogen, and the hydrogen is here. You don't have to put the hydrogen, but just to show you over here that the enolate got protonated and you added the hydrogen in there. Now if you want to go ahead, so this is the end of step one. Now if you want to go ahead and add additional H3O+, this is going to hydrolyze the ester into a carboxylic acid. And then we do heat, you take out the carbon dioxide, and you get your final product. Okay. Another example in here, still we are in Claisen, because we have an ester and we are reacting it with another ester there. So the other ester has no alpha hydrogen, this one has. So the base is going to come, take the alpha hydrogen, get the enolate. It's actually the same, repeating itself, just more examples. That enolate forms a negative charge on the oxygen, and then resonance happens, the O-ethyl is going to leave, and then it's going to attack again, form the enolate, solvent, protonates, and you're going to end up getting the final product. So that is the end up of Claisen condensation. Now, another reaction is Dickman reaction. Those reactions, they take the name of the chemists that discovered them. So Dickman is Claisen, but it is intramolecular Claisen condensation. It's the same as intramolecular aldol condensation. This is intramolecular Claisen condensation, which is called Dickman reaction. So here I do have two esters in there. Again, the same point. Choose the alpha hydrogen to make the most carbon possible, up to 6-membered rings in there. So I'm starting with the alpha hydrogen. Normally we start with symmetrical esters. So the base is going to come, take the alpha hydrogen, and create the enolate. As I did in the intramolecular aldol, I'm going to do exactly the same. Start numbering from the enolate towards the next carbonyl in there. Make the most carbon cycle. So this is going to be 5. Draw the 5-membered rings in there. So if it's 5, it's just to draw a cycle of 5 in there. And put the carbon 1 and put carbon 5. So you label carbon 1, you label carbon 5 in there, because this is the bond that you made between 1 and 5 in there. And then go ahead and number the carbons in between and fill in the gaps. So on 5, I have an O negative and an O ethyl. Just go ahead and write it down in there, because I know that with Claisen condensation, this needs to be gone. The O ethyl needs to be gone by resonance in there. So you form your carbonyl. And then you're going to use your another O ethyl to take that alpha hydrogen, create the enolate, and with the solvent, you are protonating again. And that is the end of the step 2 product. You can add to the reaction, as always, because I do have an ester, so I can hydrolyze the ester in presence of an acid, make it a carboxylic acid, do heat, take the carbon dioxide out, and I'm going to end up getting my product in there. Okay? Micheal addition, we've talked about it in chapter 18. We didn't name it Micheal back then. We named it addition to the alpha beta unsaturated carbonyls with a weakened nucleophile, and that was the last section in chapter 18. Refer to that. It is called a Micheal addition. So Micheal addition is whenever you have an enolate. So enolates are a must with Micheal addition. So you should have an enolate, and the enolate reacts with the alpha beta unsaturated carbonyl. So 2 things in Micheal's addition. You need to have an enolate. The enolate acts as a nucleophile. So when I say a nucleophile here, I mean, to make it Micheal addition, I mean that the nucleophile should be an enolate. So if this is the case, if you have an enolate, the enolate is going to attack the beta carbon of the alpha beta unsaturated carbonyl, and the double bond is going to form a negative charge on the alpha carbon. So you're going to end up having an addition. This is an addition reaction of the nucleophile to the beta carbon, and the alpha will carry a negative charge, which by any solvent can get protonated, and you can get a hydrogen in there. Okay, so your Your product is going to be simply the addition of the nucleophile to the beta carbon and eliminating, taking out the double bond in there. So let's have an example. This is called Micheal addition. So every time you see an enolate and an alpha beta unsaturated carbonyl, is going to look like this. So this is an alpha beta unsaturated carbonyl. Those two are going to make the enolate. So those two are going to make the enolate. So you start always by making the enolate. No matter what the reaction is, you always make the enolate. So I have the O-ethyl. I'm going to go ahead and react that to make the enolate with my reagent. Now notice here in my reagent, I have two types of alpha hydrogens. I do have an alpha hydrogen here, and I do have an alpha hydrogen here. Okay, now this alpha hydrogen is between two carbonyls, so it is more acidic. Because if you take a look at the structure looks like this. So you have a double bond, O-ethyl. So this is an alpha hydrogen here, and that is an alpha hydrogen here. This is more acidic because it is between two carbonyls. So an alpha hydrogen between two carbonyls is always more acidic than an alpha hydrogen next to one carbonyl. So this is why the base prefer to take this alpha hydrogen instead of the other one. You make your enolate. So the first step, always make the enolate. Once you make the enolate, in Micheal addition, the enolate is going to attack the beta carbon. So enolate comes, attacks the beta carbon, so you're making a bond between the enolate and the beta carbon, and you're going to form a negative charge on the alpha carbon that gets protonated by any solvent to a hydrogen. Okay? Here, instead of writing this as a condensed form, I am writing it as a regular structure there. But both are the same. Of course, the reaction can continue as long as I have an ester. So if you go ahead and you add H3O+, you're going to hydrolyze the ester into a carboxylic acid, and then do heat. You take out the carbon dioxide, and you end up getting your product in there. Let's have an example with all the steps. So see here, the moment I see one of my reagents is an alpha beta unsaturated carbonyl, then this is immediately a Micheal addition. So all I need now is to use this base and take the alpha hydrogen here, which is the most acidic, create the enolate. So use the base, take the alpha hydrogen, create the enolate, and then after you make the enolate, allow the enolate to attack the beta carbon in there, form a negative charge on the alpha carbon. So you have the negative charge on the alpha carbon. So all I want from you here is to not forget carbons when you are making a bond between the enolate and the beta. Okay? Don't forget carbons in there. View the molecule right. You're simply making a bond between this carbon here and the beta. So you still have the O-ethyl in there, the carbonyl O-ethyl, the ester part. You still have the carbonyl part on the other side. So everything stays the same. You're just making a new bond. This is going to be the new bond that you made over here. So that is the new bond. And then after you form a negative charge in there, you use any solvent, and that solvent is going to come and it's going to add a hydrogen to the alpha, because this was the alpha, this was the beta. Okay? This was the beta. So all I did here is I added the nucleophile to the beta carbon. I eliminated the double bond, so the double bond has no place anymore. Go ahead and continue the reaction if there are additional steps. So here, if I have an acid, that is going to hydrolyze the ester into a carboxylic acid. And then with heat, I'm going to lose carbon dioxide, and I'm going to end up getting my product. Another example, again, I do have the alpha, I do have the beta, so this is definitely Micheal's addition. I start with these two, and make the enolate. So make the enolate. CN, this is the cyanide, and we said that the alpha hydrogen here is acidic hydrogen. So the base is gonna come, take that alpha hydrogen. This is chapter 20. Okay, base comes, takes the alpha hydrogen, create the negative charge, and then the nucleophile is gonna come, attack the beta carbon, create the enolate, solvent will protonate the enolate, and you're gonna end up getting your product in this case. Reactions, you can stop here. If you don't have steps 2 and 3, you simply stop here. Okay, so right down here, this is step 2. So step 2 there, with H3O plus, I don't have an ester, but I have a cyanide, and I know that cyanide can be hydrolyzed into a carboxylic acid. This is hydrolysis of the CN into a carboxylic acid. I gave you the mechanism for, but I'm not going to ask you about the mechanism for. Just whenever you see cyanide, acidic medium, that is going to turn into a carboxylic acid. The nitrogen is going to leave in the form of an N+, and the C is going to turn into a carbonyl with a series of water, so you're going to end up having your OHs in there. And then with carbon dioxide, you're going to lose the carbon dioxide, and you're going to end up getting your product. Okay? I think this is now the last one. Now, the last one is a little bit, this one is the hardest because it's the combination of two reactions. And this one is the combination between a Micheal addition and let's see, my apologies. It's an intra, not inter, it's an intra. So please go ahead and, okay. So it's an intramolecular aldol condensation. So you start with the Micheal addition first. You create your, so you start basically, you do the Micheal addition first. And then after you do the Micheal addition, you do the intramolecular aldol condensation. And these reactions, this is what I am doing. I'm using a base. Because I'm using an aldol condensation, I'm going to use an NaOH base. I can use an NaOR as well. So, or I can use an NaOR in presence of ethanol. Any one of those can do the job in there. But always I'm going to start with a Micheal addition. So to start with the Micheal addition, I need to create my enolate and then allow the enolate to attack the beta carbon to get the Micheal addition. So you start with your enolate here. You look at your alpha carbon, alpha hydrogen, allow the base to take the alpha hydrogen. So you're going to make the enolate. After you make the enolate, you allow the enolate to attack the beta carbon, form a negative charge on the alpha. My apologies in there. I've missed a step, by the way, but so here you're going to form a negative charge on the alpha, and that negative charge is going to get protonated by the solvent, which here in this case it is water. So this one with water, so this one gets protonated with water, and you take out the negative charge. Okay, so I've just missed a step in there. So it gets protonated with water. So you're going to end up having something like this. But here, once you end up having something like this, you're going to end up having these two carbonyls that can close in a cycle. They are close to each other. So we can do an intramolecular aldol condensation. So here's why the base is going to come and attack again. And now the base is going to come and attack to make the most carbon cycle. The most up to a 6-membered rings in there. I know that I do have an alpha hydrogen here. I know that I have an alpha hydrogen there. And I know that I have an alpha hydrogen here. I'm just going to highlight those alpha hydrogens. I have an alpha hydrogen here. I have another alpha hydrogen here. And I have another alpha hydrogen over here. This is the only one that gives me a 6-membered ring. So this is why we're going to use that alpha hydrogen. The base is going to come, take the alpha hydrogen, make the enolate, and then that enolate is going to come attack the adjacent or the very close carbonyl. This is an intramolecular aldol condensation, form a negative charge on the oxygen. So basically I made a bond between this carbon here and this carbon there. This is what I did. Okay, if you want to number your carbons, it's going to be carbon 1, that is going to be carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So you're forming a 6-membered rings in there. This is carbon 6, this is carbon 1. This is carbon 2, carbon 3, carbon 4, and carbon 5. And then this is an aldol condensation. So at the end, I need to do the E1CB because I will be forming the beta hydroxy product in there, beta hydroxycarbonyl. So the ethanol is going to protonate the oxygen, make it an OH. And after that, we can do the E1CB, take out the alpha hydrogen, take out the beta OH, and you're going to end up getting the alpha beta unsaturated ketone. This is the last example with Robinson annulation. Again, you start by making the enolate. Once you make the enolate, you attack and do a Micheal addition. You attack the beta carbon, form a negative charge on the carbon over here on the alpha hydrogen, protonate in there, and then you're going to end up getting your product. Please don't stop because here you're so close to do an intramolecular aldol condensation. Again, the base is going to come, attack the hydrogen, form the enolate. The enolate will attack the adjacent carbonyl. See, if it won't attack that carbonyl over here because it's going to be very, very far away, and the maximum carbons you can form is 6-carbon ring, and then you're going to have your O negative with the solvent that's going to be an OH. You do an E1CB and you get your final product in there, which is the alpha beta unsaturated carbonate.